In this video, I want to talk about using the slope formula in order to find the slope between 2 points. And we're going to do it first numerically without using a graph, and then I'll show you what the graph will look like in each case. So our slope formula is going to be m, which represents slope, and that's the change in y divided by the change in x. So y2 minus y1 divided by x2 minus x1. So let's go ahead and look at a few examples and kind of get an idea for what this looks like and get a feel for it. So the first example, we'll have the ordered pair negative 13, 19 and negative 1, 4. And we know in each ordered pair we have an x and a y, an x and a y. And what we can do is name this first ordered pair 1 and the second ordered pair 2. So all of our coordinates will get a designation. This negative 13 will be x1, which is the x coordinate from our first ordered pair. This 19 will get the designation y1 because it's the y coordinate from the first ordered pair. And likewise, we have x2 and y2 because they're the x and y coordinates respectively from the second ordered pair. So once you have this designation, and whether you write it out or whether you kind of just know it in your mind, now we're ready to use our slope formula. So m equals y2 minus y1. So we're going to say 4 minus 19. And in the denominator, x2 minus x1, it's going to be negative 1 minus, and here we have to be really careful because what we're subtracting from the formula is actually a negative number. And that is one of the common mistakes that students make, is they don't either add the negative from the formula or they don't add the negative in here from the number itself, but we do need both. And what we'll see is when we subtract a negative, a little swoosh swoosh. So 4 minus 19 is negative 15, and then negative 1 plus 13 will be 12. And when I simplify this fraction, I can divide a 3 out of both. I'll end up with negative 5 over 4, and that will be my slope given these two initial ordered pairs, negative 13, 19 and negative 1, 4. And here's what a graph of that will look like. In this second example, once again, we're going to use our slope formula here, and here are our two ordered pairs. So let's go ahead and make our designation. So we have our x and y coordinates of our first point and our x and y coordinates of our second point. Okay, so m equals the change in our y values, so y2 minus y1. So we'll say 13 minus, and then our y1 is a negative value. So make sure we watch for that. It's minus a negative. And then our change in x's will be a negative 4 minus a negative 8. So once again, we need to have the minus sign and the negative sign. Because what happens is that we do a little swoosh swoosh up there, a little swoosh swoosh down there, and it looks like I have positive 16 and then negative 4 plus 8 over positive 4. Which I can simplify that, of course, to 4 over 1, but we don't want to write our final slope as 4 over 1. We just want to say 4. So m equals 4. Well, when you're graphing these things, 4 over 1 is very useful because it means you're going to go up 4 units and to the right 1 unit. So it's good to have the over 1 when you're using it, but as far as simplification is concerned and writing your final answer, you're going to say m equals 4. So here's the graph of what that will look like. In this third example, you'll notice our ordered pairs have fractions as our coordinates, and that's okay. It will still work the same way. So we have our slope given by the change in y over the change in x. So let's go ahead and give our designations. We have our x and y coordinate for our first point and our x and y coordinate for our second point. So let's go ahead and plug these into our formula. So y2 minus y1 will be 1/4 minus a negative 1/4. And in the denominator, we'll have the change in x. So it'll be 5/6 minus 3/2. And of course you'll see we have a complex fraction because the whole thing is a fraction. And then of course in the numerator and in the denominator we also have fractions. So let's go ahead and simplify. We'll work the numerator first. So when we're subtracting a negative, we'll go swoosh swoosh, make that an addition problem. So 1/4 plus 1/4 makes 2/4, which we can reduce to 1/2. So we have 1/2 in the numerator. And then 5/6 minus 3/2. Well, I need to get common denominators, so between 6 and 2, it looks like 6. So let's go ahead and multiply the second fraction by 3/3. So I'll have 5/6 minus, and it looks like 9/6 when I do 3 times 3 and 2 times 3. So it looks like I have for my complex fraction now 1/2 over negative 4/6. Okay, well let's kind of work down here. I know that I can reduce the negative 4/6, and that will reduce to negative 2/3. So really I have a 1/2 being divided by negative 2/3. So remember when we divide fractions, you're multiplying by the reciprocal. Sometimes you'll hear copy dot flip, or when you have it set up in this form, I do a little fraction acrobat, where the guy in the bottom is going to jump to the top, and while he does so, we're going to flip him over. So negative 2/3 is going to flip over and become negative 3/2. So yeah, a little fraction acrobat. So when this guy comes up here, this is like the copy dot flip or the multiplying by the reciprocal. Then I'm just going to multiply straight across, so negative 3/4. And that is my slope. So even though these two ordered pairs had fractions for their coordinates, the procedure we used was the same, and the process, even though we had to work with fractions a little bit, wasn't that bad. So the slope between these 2 points we found to be negative 3/4, and here's a graph of what that looks like. In this example, you'll notice our ordered pairs actually have decimals this time. Okay, so we're kind of just hitting all of our bases. So here's our slope formula again. M, which represents the slope, is y2 minus y1 over x2 minus x1. So let's go ahead and give all of our designations here. So we have our x and y coordinates, and we have our first ordered pair and our second ordered pair. Okay, so let's go ahead and plug everything in. So the change in y is y2 minus y1, so 11.41 minus 14.21. And in the denominator, we have the change in x, so 4.13 minus 5.25. Okay, so when I subtract here, 11.41 minus 14.21 will be a negative 2.8. Okay, and 14.13 minus 5.25 is going to end up being, let's see, negative 1.12. Well, I notice right away these negatives can cancel. And so I have a fraction with a decimal in the numerator and a decimal in the denominator. Well, I don't like that. So here's what we're going to do in order to get rid of the decimals in our fraction. I'm going to multiply by powers of 10. So we'll start by multiplying by 10 on the top and bottom. And remember, when we multiply and divide by 10, it moves the decimal point. So multiplying by 10 will take 2.8 and make it 28. Similarly, it will make 1.12 into 11.2. Well, with 11.2, we still have a decimal, so let's go ahead and multiply by another power of 10, and that will move the decimal point again. In the numerator, it goes from 28 to 280, okay? And in the denominator, it'll go from 11.2 to 112. And now we no longer have decimals in our fraction. So once again, the way we eliminated the decimals is by multiplying the top and bottom of our fraction by powers of 10, so we could move that decimal point out of the way and kind of shuffle him off. Okay, so now I have 280 over 112, so it looks like I need to reduce this fraction, and it seems like I can divide a 14 at least out of the top and bottom, and that will give me 20 over 8. So actually I can take a 4 out of there, and that'll give me 5 over 2. And there's my slope. Well, it kind of depends on the situation you're working with, because we started with decimals, but we ended up as a fraction. Sometimes teachers would like you to write your answer in the same form that the problem was given to you, so we might want to write this in a decimal. Or maybe if we're working with word problems, we'll want to use the decimal because it makes a little more sense. But if you do that, from this point here, you could just do the division, and you would see that the slope would be 2.5. And again, sometimes that's valuable too to have in a decimal form if you're graphing or making sense of your answer, because it's a real-world problem. But nevertheless, here's what this example looks like, finding the slope between two ordered pairs when it includes decimals. And in these last two examples, I want to take a quick look at vertical and horizontal lines whose slopes are undefined and 0. So I'm going to show you a couple of ways to look at this. The first way is just to use our slope formula like we've been using. So I'll see that m is the change in our y values divided by the change in our x values. So we'll put it this way, and then 3 minus 3. So we end up with 11 divided by 0. Well, obviously we know we cannot divide by 0, so this slope is going to be undefined. Okay? Well, what kind of a line has an undefined slope? Well, a vertical line has an undefined slope. But what we notice immediately here is that our x values were the same, weren't they? So anytime our x values are the same, we know that our slope is going to be undefined. And again, it's because it created a vertical line. So let's go ahead and look at that graph. And in our last example, you'll probably see right off the bat that our y values are the same. So this is going to be a special line as well. Let's go ahead and work our formula though first. So negative 4 minus a negative 4, and then negative 1 minus 5. Well, here we have our swoosh swoosh. So negative 4 plus 4 is 0 over negative 6, which equals 0. So if our slope is 0, what kind of line do we have? Well, we have a horizontal line. But again, we kind of knew that because our y values were the same going into it. So once again, you don't really have to work this out. If you notice immediately that your y values are the same, we know that's going to be a horizontal line, and the slope of all horizontal lines is 0. So let's go ahead and take a look at that graph as well.